In the previous episodes, we looked at React reconciliation basics. We now know what this is, why this will re-render but this will not, and what is the significance of type attribute in this object. But reconciliation is about so much more, and understanding it on a deeper level unlocks true React superpowers. How would you like to be able to write the most performant lists, fix weird bugs that no one else can, and avoid the biggest performance killer in React? All in one go. Welcome to the Advanced React course, episode 6. Today it's time to finally understand the whole picture of how React decides which components need to be rendered, removed, or added to the screen. We'll start with investigating a very interesting bug, and in the process we'll learn how React diffing and reconciliation work, look into what happens when a state update is triggered, understand why we shouldn't create components inside other components, solve the bug of two different components sharing the same state, look into how React renders arrays and why it's important to know, what is the purpose of key attribute and how it works, and when key attribute is useful outside of the lists. There will be a lot of digging into weird React behavior today. Code examples to play around with it on your own are linked in the description. Let's start with a little mystery. Imagine you're rendering a component conditionally. If state is true, render this, otherwise render that. For example, this pretty form. I want to show tax ID input for businesses registered on my website. If I check that checkbox, the field will show up, uncheck it, it disappears again. The code will look something like this: simple state and simple condition. Remember in the first episode we talked about the component's lifecycle. When a component is first needed on the screen, it's mounted. If it needs to be updated with some data, it re-renders. When it's not needed anymore, it's unmounted. The form is an example of all three of those. When I change the state from false to true, this component re-renders. When this happens, the input component is mounted and the text placeholder component is unmounted and removed. If I flip the state back to false, then the input component is unmounted, the instance is deleted and everything that was typed there will be lost. But what if, instead of a placeholder, I want to render another input? For example, to collect tax ID of a person, not a business. Same component but different props, like an ID or placeholder. What will happen? The intuitive answer is probably that the business ID component will unmount and the personal one will mount, right? If I type something and then flip the checkbox, I would expect what I typed here to disappear. Those are different inputs after all. And here's the fun part. This is not how it behaves. For some reason, the text stays where it was, as if the component is still the same. Do you know out of the top of your head why? If you're not sure, time to dive into React reconciliation process to get the answer. It's all because we don't want to deal with the DOM when we're writing front-end code anymore. Manual DOM operations is a headache that we try to avoid at all costs these days. In the past, if we wanted to update a placeholder value on an input element, for example, we'd have to do something like this. With React, we delegate all this complexity to it and write components instead. When we render a component, we expect React to convert it into an actual DOM element, put it in the appropriate place in the DOM structure, and assign all the event handlers and attributes properly. If we change the placeholder value, we expect React to find that already existing input and update it with the new value, ideally instantly. So React can't just remove the previous input and append the new one with the new data. That would be terribly slow. Instead, it needs to identify that already existing input DOM element and just update its attributes. It does so by creating and maintaining what we sometimes call the virtual DOM. This virtual DOM is just a giant object with all the components that are supposed to be rendered, all their props and their children, which are also objects of the same shape that are supposed to be rendered inside. Our input component will be represented like this. If this component was rendering something more than an input tag, the output would be an array of objects. DOM elements are represented by string type in this object. Components are represented by a type function that references the actual component. When React first mounts our app, it iterates over that tree, and if it encounters an object with string type, it converts it to an actual DOM element. If it finds an object with a function and type, it calls that function and iterates over the objects it returns. It goes through the entire tree, iteratively calling all functions until it reaches the end. The resulting DOM tree is then appended to the root element, and we finally can see our beautiful app on the screen. At some point of this app's existence, a user will interact with it, and it will be time to trigger a state update. When the state update happens, React needs to figure out what's changed because of it, and then act accordingly. It does so by creating another tree of those objects, derived from the new state value, and then comparing the new tree with the old one. In the process, it finds branches of that tree that need to be updated, removed, or can be left alone. It starts from the component where the state update was originated. It triggers this component function, gets its return tree of objects, and compares those objects with the objects before the state update. It always compares values that are sitting at exactly the same position in the tree before. It can't compare those two, for example. It starts by using shallow comparison. If the reference to this object before and after hasn't changed, then this tree is marked as unchanged and it will be left alone. No re-renders there, React will just skip the entire subtree. This usually happens when we create elements outside of the components and pass them as props. In case of our form, the reference to object before and after will be different. The objects are created locally. So React will proceed with comparison and look at the type property. If the type is the same, React will mark this portion of the tree as needs update, and re-render of this component will be triggered. Unless, of course, the reference points to a component wrapped in react.memo. In this case, it will check its props first. If the type changes, this is the signal to React that this subtree needs some radical change. So it will mark the entire subtree before as needs to be removed, unmount it, remove it from the DOM, and destroy its instance and everything that was saved inside. The subtree after will be built and mounted from scratch. Everything inside will be brand new. This is how our conditional logic from the very beginning works. When the state was true, the return of the component was this object, with this type. When we changed the state to false, the object returned is now this. Type has changed from input to placeholder. React will unmount the input and mount the placeholder, and everything we type in this input will be destroyed. If I change the state back to true, the placeholder component is unmounted and the input is mounted, with its internal state reset to empty. Which actually leads me to one very important topic that we should briefly talk about before solving the initial bug: creating components inside other components. Code like this is usually considered an anti-pattern. Now, armed with the reconciliation knowledge we already have, we can easily answer why. If we convert this into an object, what will be in the type property? It's a component, so a reference to a function. But the function is declared locally to the component. Every time re-render here happens, this function is triggered, and this function is recreated. As a result, the reference to the component in the returned object will change with every re-render. React will think that the component before and component after are different. So it will unmount input, destroy everything inside, and mount another identical input from scratch. This is what we call remounting, and usually it's pretty bad. It's at least 2 times slower than a normal re-render and causes really weird bugs, like losing focus or inability to type anything in the input. So as a rule, it's better to avoid this pattern. Back to the mystery from the beginning. We can solve it now. The mystery was this. We render 2 different input components conditionally. The expectation is If I type something in the first input and then change state, the first input should disappear, the second input appear, and what I type in the input field should be erased, which doesn't happen. Let's look at the code and try to convert it into objects. If the state is true, the return of the form component will be this. When it changes to false, the return is this. Let's trace how React will compare them. First, reference to the object. It will change since we created those elements inside. React marks this subtree as something changed. Then comparing types. Both of those are a reference to the input component. So from a React perspective, the component is the same. React now does what it was taught. Mark this subtree as needs re-render and just updates the component's data coming through the props. IDs and placeholder will change, but things like the component's instance and its internal state will be preserved, as it happens with any re-render. It's basically no different than if we rendered just one input and change its props based on state like this. There are two easy ways to fix it without major refactoring, with arrays and with keys. Let's start with arrays. Until now, we only talked about objects in the virtual DOM. But in real life, it's highly unlikely that anyone will be able to write an app where on every level of the tree hierarchy there is only one element. From time to time, we'd need to render multiple elements as siblings. Those will be represented as an array of objects. Our simple form, for example, has an array like this: the inputs and the checkbox. During re-render, when React sees an array of elements, it just iterates over it and then compares objects on the same position in the array. First with first, second with second, and so on. When we render some of the elements conditionally, they still will keep their place in the array. It's just sometimes that place will have a value null, or sometimes an object. With this in mind, let's rewrite our buggy form. Let's change the condition from this to this. This changes the render output from an array of 2 elements to an array of 3. If the state is true, the third element will be null. If the state is false, the second element turns to null, and the third one turns into an input. When React then compares those arrays, it will be a comparison of an object with null instead of 2 inputs, as it was before. As a result, the input that transitions to null will be unmounted, and the input that replaces null will be mounted. By just changing the position of inputs, the bug is fixed, and inputs behave as expected. Another way to fix this bug is with the help of the key attribute. Anyone who has ever written any list in React probably already used it. React forces us to add it when we render items from an array of data. But why? Let's convert elements to objects again. By now, I hope you will be able to do this in your sleep. It's just an array of objects with the type input. What will happen if I try to reorder items in this array? Pretty standard code. Save the order in the state and order those items based on the state. Now React will face an interesting challenge. How to detect which item is which? All of them have the same type. When I reorder them and re-render is triggered, React will be comparing items according to the place in the array, its default behavior. Type for all of them will be the same, so React will think that the component is the same and just needs props update. As a result, we'll get a pretty funky behavior if those components have some state that is not controlled from the outside. In the case of our inputs, if we type something in the first input and then press the reorder button, the text will stay with the first input. This can be solved with the key attribute. It's React's way to uniquely identify elements with the same type inside an array of children. If I add a key to those inputs, React will now compare items with the same key between re-renders, instead of their position in the array. As a result, when I reorder them, React will understand that the first item moved to another position in the array. And if I type something in it and reorder the list, the type's text will move to where it's supposed to be. The importance of the key attribute is crucial to understand when it comes to optimizing list performance. One of the most common misconceptions about the key and lists is that key is needed there for performance reasons. That adding key prevents array items from re-rendering. But as you just saw, key is not there to prevent re-renders. It just helps React to identify items in the array between re-renders, so that React can reuse the correct instance and re-render the correct component. If we want to prevent re-renders, we need to wrap those inputs in React memo, same as with any component. Now, when re-render happens, React will start comparing items before and after. We'll see that those inputs are memoized, and we'll stop and compare the props before and after re-render. If our array is the same between re-renders, and we use array's index as key, we will have this behavior. The item with the key 0 is a memoized component of the same type before and after. React will stop and compare its props. Props are the same. This component won't re-render. Same story for the items with the rest of the keys. Same type, same props. With dynamic arrays, it's much more interesting. And this is when choosing the right key plays a crucial role. What will happen if I reorder the array while using the array's index as the key? React will compare items with the same key between re-renders. Since we used the array's index as a key, they will always be in the same order. But we reordered our data. The first and second items swap places. The key value always takes priority, so React will think that props on the element with key 0 changed from business to personal, and props on the element with key 1 changed from personal to business. The result: all items in our list are memoized, but React thinks that props on all items change, so it will re-render them anyway. Memoization didn't work. To fix this, we need to make sure that the value we use in the key attribute identifies the data itself, not the place in the array. In our case, we can use ID for that. Now, when we reorder our data, the key reorders with it as well. When React compares the items by the key, it will see that none of the props on the items have changed. Memoization will work as expected, and none of the items will re-render. Exactly the same situation if we try to add a new item at the beginning of the array. If we use array's index as the key, then from React perspective, the props on the item with the key 0 will change to the new item props. Props on the key 1 will change to the props that used to be on the item 0, and a completely new item with the key 2 will appear. The first two items will re-render. The item with the key 2 will be mounted from scratch. Memoization again doesn't work as expected. If we use ID as key instead, then the items we had in the array already will have the same key and same props. They won't re-render. And only the new item with the new key will be mounted from scratch. The same story will be if we delete an item from the beginning or the middle of the array, but I will leave it to you to map it out. But why does it matter how key attribute behaves in arrays? In the original form, we don't have any lists. Because key is not limited to only dynamic arrays. It will behave in exactly the same way in any array of children. And as we already figured out, our form has one of those. When we change state and re-render happens, React thinks that input component here is the same, re-renders it instead of remounting it, and as a result, when we type something and flip the checkbox, the text is preserved. To get rid of this behavior, we need to convince React that the component that we render after the state change is a different component. With key, we can achieve exactly that. Now, when this component re-renders and React compares elements in the array, it will see that the element with the first key disappeared. That means this component needs to be unmounted and its instance should be destroyed. And a new element with the new key appeared. This component will be mounted, and its instance will be initialized from scratch. To our eyes, it will appear as if the input state is reset to empty when we check the checkbox. This technique is also known as state reset. As you can see, it has nothing to do with state per se, but it's sometimes used when there is a need to reset the state of an uncontrolled component, like our input field, to a default value. You don't even need arrays for this technique. It will work on any element with the key attribute. If you want to force a state reset on URL change, for example, it could be as simple as this: getting the current URL from the router and passing it as key. The thing to be mindful here is that this technique is not state reset per se. It actually forces React to unmount a component completely and mount a new one. For big components, that might cause performance problems. Mounting is usually much slower than a simple re-render. This is not the end of the key story, by the way. There are a few more fun facts and little quirks. For example, we can use key to force React to reuse an existing element. Remember how we fixed the initial bug by rendering the input element in different positions in the children array? When state changes from false to true, the element on the second position changes from null to input, and the third one changes from input to null. As a result, the first input is mounted, the second is unmounted, and the state between them is not preserved. Watch what will happen if I add a key attribute to both of them with the same value. Now we have an input type with the same key changing its position from the third to the second place in the array. React will think it's the same component, reuse already existing instance, and all the state between them will be preserved. Or another fun fact. Have you thought about why React never forces us to use a key attribute to anything other than a list of elements? This code and this will produce exactly the same result when we convert them into objects. An array of children, each child has input type. But how come React complains when we didn't add the key to the first example and doesn't care about it in the second? This is because the first array is dynamic. We can programmatically change the number of elements there or change the element's position in the array. We can't do that with the second example. Even if we render some of the items conditionally, the number of items there will be constant. Just some of them sometimes will be null. But wait a second. How React even detects that this array is dynamic? On the surface, it looks like a simple array. What will happen if I render an item of the same type after the dynamic array? Will it be part of the array and follow the rules of the key there? That could be problematic. Fortunately, there is nothing to worry about here. When we mix dynamic and static elements like this, the dynamic array will take place of one of the elements in the static array. We'll get an array inside another array if we convert this structure into objects. The fact that the array is nested will be our indication that this one is dynamic. The input that we added manually will always be on the same position in the root array. This is more or less it about diffing and reconciliation in React. At least the part that is most useful for our everyday life. Don't forget to play around with the code examples linked in the description. And in the next video, we will take a break from re-renders and talk about higher order components, what they are, how they work, and whether we still need them now that we have hooks.